Okay, so now in the last class we have seen decoder, encoder and all. That is unit number 4, code conversion using decoder, IC. But now what am I going to tell you is only code conversion, implementation or realization of the given code converter circuit by using logic gates. In the next class we will see how to implement the same circuit by using the decoder IC 74HC138. Okay, so now it's an octal to XS3 conversion. Okay, octal to XS3 conversion, and this is the decimal number. Octal is nothing but 0 to 7, meaning 8, the base 8. Octal is base 8, right? So from 0 to 7, and this is ABC, the binary version I have written here, 0 0 0. From 0 to 8, the octal and the binary is same. The octal and the binary number is same. Okay, so that is what I have given here, the equivalent binary number, so the equivalent octal XS3 code. Okay, XS3 code, that you know. So the XS3 code also we have given here, namely for 0 0 0 it is 0 0 1 1, and 0 0 1 it is 0 1 0 0. Okay, and then XS3 is nothing but this number plus 3, right? This number plus 3, that you know. So 0 0 0 0 plus 3, it is 3. So the equivalent binary is 0 0 1 1. Okay, and then 1 plus 3, this is 1, no, 1 plus 3, that is 4, that is 0 1 0 0. Okay, so octal to XS3, you know that from decimal number you just add 3 to the decimal number. Okay, that is your XS3, fill up your XS3 code, because output is, this is your output lines. So you have 4 output lines of octal, that is x1, x2, x3 and x4. We are naming it as x1, x2, x3 and x4. For time being you don't see these three because in the next class we will see how to implement the same circuit by using decoder. Now as far as today's class is concerned, we have 3 inputs pins A, B, C, and we have 4 output pins x1, x2, x3 and x4. Okay, x1, x2, x3 and x4. So now how many K maps we need? We need 4 K maps. So the inputs are nothing but the 4 K map. How will you do? Here let me write the K map. Okay, so the inputs are only A and B, C. Okay, 1 2 3 4, and again you have an input here, 1 2 3 4. So A, B, C, 0 1 0 0 0 1 1 1 1 0. So this is A, B, C, D, whereas this is for the x1, and this is for the output x2. Okay, output x2. First let me write what are all the things, min terms for which your x1 is 1. So sum of min term it is equivalent to 5, 6 and 7 decimal. So 5, 6 and 7 decimal, and then yeah, and then your x2 is equivalent to your binary sum of min term, for which min term your things are 1, So I am writing here x2. x2 is nothing but, for which minterms my x2 is 1, it is 2 and 3 4 I'm sorry, 2 3 and 4. Even 1 is there. Okay, so 1 2 3 and 4, and come here. So here you have 0 3 4 and then 7. Okay, and then go ahead with x4. Sum of min terms 0 2 4 and 6. Okay, 4 and 6. Am I right? So now let me fill this truth table. 1 is 5 6 7. 1 is 5 6 7. This is 0 1 2 3 3 2 and 4 5 6 and 7. 1 is 5 6 and 7. And what about 2? 2 is 1 2 3 4. 2 is 1 2 3 and 4. Okay, and then and we know this already. This is 0 and this is 1 0 0 0 1 1 1 and 1 0. Okay, so let me complete this first. How will I do this? So this is 1 and whereas this is 2. Okay, so how will you write this? Whereas this is A, the x1 is equal to A, and the common thing here is C, plus, and here again A, and the common thing here is B. Okay, so here I can write it as A into B plus C. Okay, and then go ahead here. This is x2. x2, I may have 3 combinations, 1 2, and this is left as such. Okay, so now let me write it here. x2 is equal to, and this is A bar C plus A bar B plus ABC. Okay, ABC. Here again I can take A bar commonly out, B plus C plus ABC. Okay, this is my x2. For x3 and x4, again ABC 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0, and this is 0 1 2 3 4 5 6 7. Okay, and for x3 0 3 4 7. 0 3 4 7, and for the next case it is 0 2 4 6. 0 2 4 and 6. Okay, so it is easy now. This one, it's a 4-bit combination. I can combine this and this together. If I fold this paper from left to right, if I fold these four, can make a combination of 1. So this is nothing but here I will have change in A. So common thing is C bar. So x4 is C bar, and come to x3, I can have only this 2-bit combination. So this is B bar C bar plus BC. So this is your B XNOR. Okay, complement of XOR is XNOR. For similar inputs you have 1. This is x3. So now we know this x4, x3, and then this is our x1, and this is our x2. Okay, even simplification is possible here. Let me check here. Okay, instead of taking like this, I can take B commonly out, A bar plus AC, A bar C. So A bar C plus B into, this one can be written as A bar C. So A bar C again into 1 plus B. 1 plus anything is 1. So finally x2 is A bar C. Okay, see here I have taken this B commonly out. This is A bar AC, and this is from the Boolean law. A bar plus AC can be written as A bar and then the C if the complement is available here. So I can write it as A bar C. So again here I can take it as A bar C commonly out, 1 plus B. 1 plus B is 1 again. So x2 is AC. Okay, so we know the expressions now. What are all the expressions we have? So let me write it down here. What are all the things? Output. Let me write it down here. The expressions. Consolidate and let me write x1, x2, x3, x4 can be written as x4 is C bar, x3 is B, x naught C, whereas x1 is x1 is A into B plus C, and x2 is A bar C. Okay, so if I implement here, I need an and then an AND, or is nothing but BC, AND is A, so this is x1. Okay, so if I take an inverter, this is A bar, and again I need an AND. This is C, this is A bar C, and then from here I can take B. It's an XNOR. Okay, so again B C, and then if I take an inverter, this is C bar, which is equal to x4. This is x3, whereas this is x2. Okay, this is how we will be implementing the XS3 to design and implement a Octal 2. Okay, a Octal 2 7-segment display Okay, 7 segment display. Design and implement octal to 7 segment display. Okay, so 7 segment display, only the first 8 numbers of octal number, because if we go ahead then it will be complicated. So G. So let me take the input of octal as A, B and C, and the output are these 7 segments. So 1, 2, 3, 4, 5, 6 and 7. Okay, we need to develop the truth table first. So for that, these are LEDs, right? Behind the segments there will be LEDs, so you need to drive the LEDs. So A, B, E, C and D is the 0. So which are all the segment active? Active segments are A, B, C, D, E, F. Let me write it again. 0, 1, 2, 3, 4, 5, 6 and 7. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So except the segment G, everything is active. Okay, except the segment G, everything is active. Okay, and for 1, F and G will be active. Okay, for 1, F and G will be active. F and G will be active. And for 2, A, B, G, E, D. A, B, G, E and D. See, I'll repeat here. So 2 you will write like this. So this is A, B, G, E and D. Okay. And similarly for 3, A, B, G, C, D. A, B, G, C, D. And for 4, how will you write your 4? These two, this one and this one. No, I am writing it ulta, right? So 4 is this, namely F, G, B, C. Okay, F, G, B, C. F, G, B, C. Okay, and then for 5, it is A, F, G, C, D. A, F, G, C, D. And then 5 is this. Okay, 6 is this. So this is, except B, everything is active. Except B, everything is active. And for 7, A, B, C. A, B and C. The rest all is 0. Okay, so this is done. So let me fill up this A. A is nothing but sum of min terms. So 0, 0, 2, 3, 5, 6, 7. 5, 6 and 7. Okay, and we need C 7 K maps, 1, 2, 3, 4, 5, 6, 7. So then B is nothing but sum of min terms 0, 2, 3, 4 and then 7. And C is nothing but sum of min terms 1, 3, 4, 5, 6 and 7. Okay, and D is nothing but sum of minterms 0, 2, 3, 5 and 6. Okay, whereas E is nothing but sum of minterm 0, 2, 6, and F is nothing but sum of minterm 0, 1, 4, 5, 6, and whereas G is nothing but sum of minterms 1, 2, 3, 4, 5 and 6. Okay, so for all this minterms, what you need to do is you need to develop and realize, implement the logic circuit. Now you know, so A is the input now, and it's 3 variable map, right? Octal. So again this is 1, 2, 3, 4. The inputs are A and B, C. Output is segment A 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Let me do it for only A and B. So 0, 2, 3, 5, 6, 7. 0, 2, 3, 5, 6, 7. Okay, this is for A. And whereas the next segment B, A 0, 1, B, C 0, 0, 0, 1, 1, 1, 1, 0. For B it is 0, 2, 3, 4, 7. B is 0, 2, 3, 4 and 7. Okay, so how we will combine, and all this 4 can be clubbed. Okay, all these 4 can be clubbed. And then these 2 and these 2. Okay, whereas here you can even take like this. You can even take like this. See, this 7 segment display, I need to tell you one more thing. This 7 segment display, other than the numbers from 1, 2, 2, 3, 4, 5, 6, 7, 8. Okay, it can display like this. It's a single LED chip, right? 9, and then A, B, or even B can be like this, B, C, D is similar to this, D, A, 0. Okay, D, E, F. Okay, so these are all hexadecimal. Up to hexadecimal, from 0 to 16 you can display here in this single LED chip. Okay, in this single LED chip. So from A, these are all your hexadecimal numbers. So here even we can take in the table, see, from 8 to 15 they are don't care conditions. This don't care conditions can be used for simplifying your given logical min-term expressions. So instead of having this 3 2 power 3, which is this 3 variable k map, we can go ahead with 4 variable k map, because we can implement this even with the 4 variable map. Okay, so if it is a 4 variable map, okay, I'll be having one more variable here, right? I'll be having one more things here. Instead of a b c d, let me write it as y here, okay, and variable y. So this will be 0 all for all, because it's an octal, everything will be 0 only. So for all it is 0 only, okay. For all the most significant bit of the input octal, it will be 0. So I will write it as yx, ya, yabc. So 0 0 0 1 1 1 1 0. So again the same thing, but from 8 to 15 it is don't care. For all the k map table, namely from A to G, 8 to 15 can be used here for don't care conditions. So 8, 9, 10, 11, 12, 13, 14, 15. These are all don't cares. This can be used for the reduction. Okay, for the reduction. If I see this, look here, this 8 variable I can combine one, this is one, okay, and this one, this is a 4 variable one, I can combine 2, and the third one, okay, and the third one, 4 corners, if I fold like this, I can combine. So this A can be written as, okay, this 8 which is common, this is BC, right? So B is common, and for this 4 variable, A is common, and here C is common, plus, and for the 4 corners, A is, Y is changing, but A is common, so it is A bar, and for the first and the last column, C bar. Okay. So what am I trying to say you is, you can use a 4 variable k map for getting a simplified expression. Getting a simplified expression. These are all X don't care conditions. Okay. So it's very much easy now. Now this is one 4 variable, another 4 variable, and the third one I can go ahead like this 3. Okay, the combination is simple with minimum number of variables. So this is B bar C bar plus BC. This is for segment B, and plus, and this is B, and whereas this is A bar. Okay, so this B bar C bar plus BC can be written as B X naught C plus BA bar. Okay, I have done for 2 things, namely for A and B. Okay, namely for A and B. The rest you can complete by yourself. For all the other segments you can complete by yourself. Keep in mind from 8 to 15, keep it as don't care condition, and then solve for the other things. Then try to implement it by using logic gates. Okay, thank you. With this I will stop today.